So welcome back, everybody. And I wanted to bring up a little bit of some of the topics which we discussed last week with the singular value decomposition. And the aim is to try to make an analysis of ridge and lasso regression and try to understand that in terms of a singular value decomposition. And then we're going to relate that to ordinary least squares. And one of the things which becomes important for us is actually to understand the fact that these methods can be used to reduce some of the features, the importance of some specific features. So if you have, let's say, 30 features, not all of them may be relevant to describe your data. And lasso and ridge, by this hyperparameter, they can allow you to tune away some of the features. Which ones? We don't know a priori. So that means that later when we're going to see a method which is called principal component analysis, that's another way by which we can look at the correlation matrix and try to, by looking at the eigen values of the correlation matrix, we can actually then say something about which feature are less important and which are more important. So there are many things which are interlinked. So what I want to do now is to build up this kind of basic steps so that you can start to see the bigger picture. Okay, but the thing which we discussed last week with the ridge regression, we presented that as a way to get rid of the problem with the matrices which could have a determinant which was zero, or singular matrices as we call them. So the singular value decomposition is a way by which we can decompose even a matrix which is singular. That decomposition can always be performed, and it allows us to calculate something which is called the pseudo-inverse. And when we normally invert the matrix in ordinary least squares, but also in ridge regression, we normally call an algorithm which is called P-inv, which is actually the pseudo-inverse, based on a singular value decomposition of the matrix. So the singular value decomposition algorithm allows us also to bring in some of these important elements from linear algebra. And it's an algorithm which I think it's one of the more fantastic ones when it comes to linear algebra. It simply tells you that even if the matrix is not quadratic and if it's singular, you can always perform a singular value decomposition. So let me quickly bring back some of the things which we did last week. And we are going to just look back at the Jupyter notebook. So let me just find that one. I should have it somewhere. I had my, here we are. So the what we did last week was to present the ridge and lasso regression methods. And we went through the way we would derive them, the way we introduced this hyperparameter. So when we moved away from ordinary least squares to ridge regression, what we introduced then was the norm 2 of the unknown parameters beta, and we added a parameter lambda. So in many cases, what people do is actually to put a constraint on the parameters lambda so that the sum over these beta values are less than a specific value, so that the sum here doesn't diverge. So this is the sum over the beta value squared. And this is the definition of the norm 2. And then when you square it, then you have these parameters beta squared. And then the other method is something which is called lasso the regression. And with lasso the regression, when we take the derivative of the cost function with respect to beta, we have to introduce an if test. And we cannot extract a simple analytical expression for the unknown parameters beta, as we did with the ridge regression and ordinary least squares. Because then suddenly we have an if test, and we have to test whether the value of beta is less than 0 or whether it's larger than 0. And then we put it to +1 or -1. Then the problem we have is that you have a discontinuity when beta is equal to 0. And many practitioners just put the value to 0 there. So the thing which we did last week was actually to go through that, but we also started to discuss the singular value decomposition. So let me bring that back with the slides which we had last week. So we started to look at the basic mathematics of the singular value decomposition. Can you all see well here? There's no problem with seeing the screen. I can move away a little bit so you see it a little bit better. Now, the thing with the singular value decomposition is that we can always decompose a matrix in terms of two orthogonal matrices, U and V, and the matrix which contains the singular values. And this specific example which you see here is an example where you can immediately see that the determinant of this matrix is actually 0. And it produces also an eigenvalue which is equal to 0. But this matrix here, even if we cannot find the inverse of the matrix, we can always perform a singular value decomposition of that specific matrix. And one of the things we did then last time was actually to generate the singular value decomposition. So what I did here was actually to run the singular value decomposition, which you find in NumPy, for instance, or any library like LAPACK, linear algebra package, which allows you to call a function which sets up the singular value decomposition. So this first one, in this case, we have a square matrix, and the first matrix here is the matrix U, and you can easily see that that is a unitary matrix. This contains now the singular value, so 1 is 2. So it means that the rank of the problem is 1, not 2, which is a dimensionality of the matrix. It's a 2 by 2 matrix. And you see you have this one value here, which is 0. So you cannot escape the fact that you have singularities. But you will then have singular values, which are larger than 0, and then you will have a set of values which are 0. So let me just quickly go down a little bit here. There are codes for doing the singular value decomposition, but I wanted just to now to switch a little bit back before we look at the codes, just to go back and look at some of the mathematics of the singular value decomposition, and why that is of interest for ordinary least squares and ridge regression in particular. And we can actually use that to gain some insight about what is going on mathematically here, so that we can try to get some feeling of what is the difference between ridge and ordinary least squares. In both cases, we have analytical expression for the parameter beta. But with the singular value decomposition, we can actually make a mathematical interpretation of what the ridge and this parameter lambda is doing for us. So let's try to just go down and look at the whiteboard. And then we're going to go back and look at the codes and see how we can implement the singular value decomposition and how we can use that to calculate what's called the pseudo-inverse. So let me bring that back. So if we look at the singular value decomposition, what we have is the following. So we have defined a matrix, which we called X, which could be our design matrix. And we have assumed that this matrix has a dimensionality of n times p. That means that when we look at the matrix which could lead to problems, when we want to calculate the inverse of the matrix, X transpose times X, this is a matrix which has dimensionality p times p. Now, if we now assume that we have a singular value decomposition, we can always, even if this matrix X is singular, or the matrix X transpose times X is singular, we can always perform a singular value decomposition. So that means that we can rewrite this matrix in terms of this matrix sigma and unitary matrices U and V. So let me just quickly repeat that about the matrices. So if I have a U times U transpose is the same as U transpose times U, and that gives us the identity matrix. And I have V transpose, So that's also equal to the identity matrix. And then the matrix U has dimensionality n times n. And V has a dimensionality of P times P. So these are square matrices and unitary matrices, orthogonal matrices. And the matrix sigma has a dimensionality of n times P. And sigma is a matrix which then contains the so-called singular values. So sigma 0, sigma 1, and all the way down to sigma P minus 1. And then the rest of the elements are 0. And this sigma 0 is larger than sigma 1, larger than sigma 2, and larger than sigma P minus 1, which assume to all be larger than 0. So I'm not proving the singular value decomposition theorem. We are just going to use it in our context here. Now, if you now look at the matrices U, we can rewrite that in terms of the vectors. So we would have the vector U0. So I'm just bold-facing this to indicate that these are vectors of UN minus 1. So these are just the columns of the matrix U. And similarly, we have the same thing for the matrix V. So we have V0. Again, I'm trying to bold-face this to indicate that these are vectors. Sometimes it's not easy, so this should be P minus 1, like that. So then, one thing to notice now, when we are going to make this analysis, what we are going to do now is actually to rewrite the design matrix in terms of a singular value decomposition. So when we now take and compute the quantity X transpose times X, this is going to be given by U of sigma of V transpose, and then this is being transposed, and multiplied with U of sigma of V transpose. So that means that what I'm going to get then is V times sigma transpose, and then I have U here, and then I have a U of T, U T here, and this is multiplied with sigma of V of T. Now, this is a unitary orthogonal matrix, so that means that this just gives us the identity matrix. So this is given by V of sigma T times sigma times V of T. Now, if we now look at the matrix sigma, so sigma, just to remind you, has dimensionalities n times P. So that means that if I take sigma transpose times sigma, that has dimensionality P times P. So notice now that what we are doing is actually to obtain a matrix X transpose times X, which has the right dimensionality through, because the matrix X transpose times X has dimensionality P times P. So we are actually getting a matrix which has the correct dimensionality here. Now, before we move on now, there's something which is interesting to look at. So I should also say that this sigma tau, sigma transpose times sigma, when we do the mathematics here now, it's just going to be sigma squared, sigma 1 squared, down to sigma P minus 1 squared. And all the other ones are 0. If I take the other operation, which we're going to need just in some moments, this is going to have a dimensionality of n times n. And that will contain also the matrix elements, or the so-called singular values, which are 0. But let's just stay with this for now. Now take a look at, so what we did was actually to rewrite this now in terms of a matrix V, the orthogonal matrix, times sigma transpose times sigma, multiplied with V of T. There's one small intermezzo which is actually a little bit interesting for us. So let's just do that before we move on. if I multiply from the left or from the right with the matrix V, so what I could do now is to multiply from the left or from the right. Let's do from the right with V. So what I will have then is the following. I will have X transpose times X multiplied with V, and that's equal to V times sigma transpose times sigma. So if I now look at one of the vectors, remember now that V is given by, it can be represented in a compact way with the column vectors. So just pick one of these vectors now. And then if you look at what you have that X transpose times V of I is equal to V of I. But then what I get is sigma I squared, because that's a diagonal matrix, which now contains the, if you look at sigma t times sigma t, you have this matrix here. So if I just look at one of the column vectors which define V, this is nothing but an eigenvalue problem. Would you agree on that? Now, there's an interesting thing here. And if you look at this problem now, this means that the eigenvalues of X transpose times X are the singular values squared, the so-called singular values. And in this case, since we are only looking at the non-zero singular values, it means they are all larger than zero. So we don't need to calculate the eigenvalues of X of t in order to figure out whether they're larger than zero or not. This is an interesting property, because that means that the matrix xt times X is positive definite. This is, I said this is a kind of intermezzo, but it's a very useful one, because we know that the second derivative of the cost function with respect to the vectors b, beta, t is actually equal the way we define the cost function for ordinary least squares. So I'm going to put OLS here. That is equal to this quantity, X. So all the eigenvalues of this matrix X transpose times X are positive. This means that the second derivative is going to be positive. And if it's positive, it means that we have a convex problem in the optimization. And all the eigenvalues are positive, which again means that this is a problem which is going to have a global minimum, which is defined by the largest eigenvalue or the largest singular value. So that means that we have a, since this is a second derivative, we discussed this in the beginning, this means that it's a convex function, convex problem with a global maximum. So this was just a small intermezzo, which we can actually derive from the expression for the singular value decomposition. Any questions so far? Yeah. Because if you have many components of the matrix. So that means that if you have 100 parameters, your matrix is going to be 100 by 100. And there will be minima for each one of these parameters. But there will be one minimum which is defined by normally the largest eigenvalues. Yeah, just one global. Oh, sorry, I brought. minimum. Sorry. Thanks. Yeah, this is the thing. You think of something and you write something different. Thanks. So this was just, I mentioned this in the very beginning, that for the ordinary least squares, this is actually going to be a minimization problem of this type. And you will also see when you have ridge regression, if we go to that, in ridge regression, what we need to invert then is actually a matrix of the type xt of x plus lambda times the identity matrix. And in ridge regression, what we are going to get is actually that the second derivative is now going to contain this parameter lambda. Since this lambda is positive, it means that all the eigenvalues are again going to be positive. So ridge regression and ordinary least squares are also going to give us, are both going to give us a problem which is a convex optimization problem. So also, and you can easily see that when you calculate the second derivative of the cost function for ridge, that means that also this is also a convex problem with a global minimum. So it means that for both these type of cost functions, we are not going to run into problems with not having a global minimum. The problem is more whether we will be able to reach that global minimum. Now, there's another small intermezzo before we move on to the analysis of ordinary least squares and ridge regression in terms of the singular value decomposition. So let's call this intermezzo number 2, because this is also a very useful property. Now, we saw that the eigen values of xt times x multiplied with v of I is actually equal to this sigma I times v of I. There is a matrix which we can actually, and this is independent of whether we do ordinary least squares or ridge regression or whatever. And this method or this property is actually something which we are going to study again and again. And you guys have probably heard about the covariance, have you? Is that something which rings a bell? No, is somebody who's never heard about the covariance? So the covariance measures the correlation between the different features which we have. So if we look at the covariance, let me just quickly define that. If I have two variables, x of I and x of j, if we have a continuous function, this is going to be given with an integral over the domain and over dxi, dxj. This is going to be multiplied with x of I minus mu of I, the mean value for the variable I, and x of j minus mu of j, multiplied with the probability of finding x of I and x of j. This is the definition if you now have the probability distribution. And this quantity here is 0 if you have identically distributed and independent variables. So if this xi and xj are id, which in this case means that px of I of px of j is actually equal to the probability, then these variables are uncorrelated and the covariance is actually equal to 0. Now, since we are setting up the design matrix, so for the design matrix which we have, X, this is a matrix which we can write out in terms of the column vectors. So we would have X0, X1, X2, etc., up to XP minus 1, where the P's are the features which we have. So remember, the way we set up the design matrix is that we have on the rows, we have the different input variables, but then we can have different features. And the type of example we looked at was a polynomial approximation. And then every column represented the polynomial to a given degree. If you look at a classification like this classification problem like this cancer data, each column could then represent a specific feature, like the size of the tumor, the thickness of the tumor, the color of the tumor, and so on and so on. So when we now look at the covariance for this matrix X, so I'm just going to write it like that. Mathematically, this is going to be defined as the sum over n, and now I'm using this unbiased sum because else you would find it as n minus 1. And it contains now, and I'm looking at these, I'm just picking these different vectors. So I would then have, let me just rewrite this one quickly here. If I look at the covariance of these quantities xi and xj, when I have a discrete variable where I don't have the probability distribution, because now I'm just looking at the sample covariance, this is going to be defined as a sum over k. So I'm going to have the matrix elements. So these are now the vectors. Keep that in mind. So it could be any of these vectors in here, which we are looking at. So the sum over k runs now from 0 to n minus 1. So these are the different elements in the design matrix. So that means that what I would have then would be k of I minus mu of I multiplied with x k of j minus mu of j. So remember now that the design matrix X contains elements x00, x01, x0 p minus 1, x10, down to xn minus 10. Here I have x minus 1, 1, and this goes all the way up to xn minus 1 of p minus 1. So in each case here, this would just be the vector x0, and this is obviously the vector x1, etc. It takes always some time to readjust your mind between vectors and matrices and then specific elements of a matrix. So the covariance for these two vectors is now defined by this sum here. And then it's easy to see that the covariance can actually be written out as, and now I'm just writing, I'm going to let this xj between two different components. I'm going to let this be the covariance of the matrix X. So I'm going to use a shorthand notation, and this is going to contain all the column vectors which we have. And this is nothing but 1 divided by n, and it's easy to see that this is given by x transpose times x. So I leave that as a small exercise. Just convince yourself from the expression which you see here that this can be translated into this term here. So now I'm just looking at the covariance of the matrix X. That means that I'm looking at all the possible products between the different vectors, the column vectors of the matrix. And you can actually show that this is equal to the transpose design matrix times the design matrix. So this is the covariance matrix. Now, if you divide the diagonal matrix elements by the variance of each vector, you will get the correlation matrix. So people normally don't look at the covariance matrix because the covariance can be large. It can take negative values and positive values, which can be large. The correlation matrix, when you divide by the variance, is going to have only ones, the absolute value of 1 along the diagonal. So people tend normally, when they are analyzing the correlations between different data points, they are looking at the correlation matrix. But keep in mind, so this covariance tells you how much correlated these vectors are. So if there are zero correlations, that means you can treat them as two independent variables. If there are strong correlations, it means that these could affect clearly the output of a given experiment or data set which you have. So if you're looking at housing prices, what you would typically see is that the median value of the house is, as you would expect, is strongly correlated with the number of rooms you have in the house. You would expect that. And if you were given data by housing prices and you calculate the covariance or the correlation matrix for the housing prices, you would find, or just for all the data you have, the median value, the number of rooms, where the house is located, etc., the number of bathrooms, you could have that as a feature. And when you calculate that, you will see that the median value is strongly influenced or strongly correlated with the number of rooms the house has. Just one example of what the correlation matrix actually tells you. And in machine learning, the reason why I'm bringing this up is that in machine learning, you're interested in correlations. And you're interested in making predictions. When you fit the model, you would then make predictions about data which has not been included in the training. But then you can also say something about the correlations between the different features. So if you look at the cancer data, one of the features is the radius of the tumor. Another one is the area of the tumor. And you would clearly expect, since the area is proportional with the radius squared, you would expect that these two properties are correlated, and they are indeed. So the thing with ordinary least squares is that in ordinary least squares, this matrix here is actually proportional to the unknown parameters beta, or the optimal parameters beta. But that's only a special case. In most methods, the parameters which we derive are not proportional to this quantity. So that's a special case with ordinary least squares. But the thing which is interesting now is that you know that the eigenvalues of this quantity here is given by the singular values from the singular value decomposition. So this quantity here is proportional to, or has eigenvalues. So the eigenvalues of the correlation matrix or the covariance matrix, the eigenvalues are proportional with the singular values, sigma I squared. Now, if you look at the covariance matrix, there's an interesting thing here, which if we diagonalize this matrix X transpose times X, what you're doing when you diagonalize is that you perform a set of orthogonal transformations. So at the end, you have only diagonal values when you perform these orthogonal transformations. If you now look at the diagonal elements of this matrix which you have here, without me having set up the matrix elements for you, by you just looking at this one, when you take xi times xi, what kind of quantity is that? If you take xi times xi here, there's a famous quantity. It's not the mean value, but it's a quantity which we often list together with the mean value. Exactly. The diagonal elements of this matrix here are given by the variance. So when you have the full covariance matrix, these diagonal elements are not the eigenvalues, right? because the non-diagonal matrix elements may not be zero. However, when you diagonalize, you're performing a unitary or orthogonal transformation till the matrix is diagonal. So that means that the matrix elements along the diagonal here, when you diagonalize, the eigenvalues will most likely be proportional, but they will actually be a kind of modified variance for you. And this is an important feature when you move to a method like the principal component analysis, which is used to eliminate specific features. And you normally eliminate the features which have the smallest eigen or singular value, which means normally the smallest variance. So we are coming back to that a little bit later, because that's a so-called unsupervised method for getting rid of unwanted features. So by calculating the eigenvalues of the covariance matrix, you could then say that if the eigenvalue is smaller than 0.1, I'm not interested in it. And I only keep those values which give me a total variance of, let's say, 90%, just to give you an example. This is often used to take away specific features and reduce the dimensionality of the problem. Because sometimes you can have millions of features, but only 5 or 10 of them are interesting for a specific problem you're looking at. And then clearly you can reduce the dimensionality of the problem from, let's say, 100,000 to 10. And this is often done in this covariance analysis. So this was a digression. But you see now that you can actually, if you have done a singular value decomposition, you have automatically, in this specific case here, you have immediately a proof that your matrix is positive definite, your design matrix. And if you're dealing with ordinary least squares or ridge regression, you know that there is a global minimum. And two, if you now are interested in correlations in your data set and you want to reduce the dimensionality, you can obtain the eigenvalues of the correlation matrix by a singular value decomposition. So these are just what I normally call this kind of small hidden gems, which hopefully add to a little bit more insight into what these kind of methods mean and the kind of analysis which we can make based on that. So I can see it doesn't sound like the most exciting topic. I find it exciting. I hope I could convince you guys. So what we're going to, yeah?
Can you repeat what you told about, I mean, when you diagonalize X transpose times X,
yeah,
then I don't quite understand the meaning of the eigenvalues of that matrix. Because I mean, in the normal matrix, you have the autocorrelation and the diagonal.
Yeah, so let's just look at, so if you look at the covariance of X, when you write it out, you're going to have the variance, which in this case we call sigma squared. This is not the singular value, so we should be a little bit careful. It's given by that. And then you have the covariance here of x0, x1. So these are just matrix elements, right? And then you have covariance of x0 of xp minus 1. That's the last one. And then down here, you have sigma p minus 1 squared. So this is the variance. And then sigma 1, so it's not a singular value. And then you have all these non-diagonal matrix elements. Obviously, if you have no correlations, then the matrix is diagonal. It's only the variance which you have on the diagonals. But when you diagonalize this matrix, what you do then is that you perform a set of unitary transformations. So you would have a transformation S multiplied with the covariance of X, of S of T, which at the end is diagonal, right? So this quantity which you're transforming now is actually you transforming to another basis where you only have the variance along the diagonals. So that means that what you have here are going to be sigma 0 tilde of sigma squared, sigma 1 tilde.
So it's not the same.
Yes, it's not the same.
Okay.
And then you have zeros, right? So what you're bringing into these eigenvalues is a mixing from these different matrix elements by the unitary or orthogonal transformation. So what you have, if you now define another matrix Y, which is diagonal, you can relate that one to your other matrix by a singular, by unitary transformation or orthogonal transformation. So what you could think of now is a covariance of a matrix Y, which is actually this given by this transformation here of a matrix X times S of t. And you know, when you're diagonalizing a problem, you just perform a series of similarity transformations. Now, what happens when you do these transformations is that the eigenvalues, when you want to calculate the eigenvalues, you know that the eigenvalues stay the same. So if you take a matrix problem, A times X equal to lambda times X, you know that if you have a matrix S, a transformation with an orthogonal matrix, where this becomes a diagonal matrix, you know that the eigenvalues, they will be preserved, so they are the same, but what change are the eigenvectors by these unitary or orthogonal transformations. So you would have a lambda 0 down to some lambda n minus 1, if that is the dimensionality of the matrix. But you can see that the eigenvalues stay the same, because if I multiply from the left, this matrix, times X equal lambda times X, and in here, since I have defined this matrix to be a singular, an orthogonal or unitary matrix, I can always insert 1. This is equal to ST times S. So here I should have S, which becomes lambda, is just a constant, times S times X. If I insert the identity, I have S transpose times S of X equal lambda times S of X. This is a new eigenvector, Y, and this is a new matrix, B. So I have B times Y is equal lambda times Y. The eigenvalues stay the same, but what changes are the eigenvectors. So that's the typical approach which you do when you want to diagonalize a matrix. So what it means is that if you have found the eigenvalues by the singular value decomposition, these are the eigenvalues of your covariance matrix. And that's an interesting aspect, because if you do the singular value decomposition, you can say something about specific features. And now after the break now, we are actually going back to OLS and reach in terms of with SVD. So what we found, let me just write this up, is that we could write this as V times sigma transpose times sigma times V transpose. Now what we have is that beta, the optimal one, is actually given by X transpose times X inverse. So this is ordinary least squares times X transpose times Y. Now what we can do next now is to look at Y tilde, which is the same as X times this quantity here. And that is equal to X times X transpose times X minus 1 X transpose times Y. I do the singular value transformation. So this is going to be U of sigma of V of t divided by V sigma transpose sigma V of t minus 1. And this is multiplied again with a transpose here, which becomes V of V multiplied with sigma transpose times u of t times y. And after the break, I'm going to simplify this one. And you are going to see then at y here is going to be a projection of the original y tilde is going to be a projection of the original y defined by the column vectors of the orthogonal matrix U. But you're not going to have all the column vectors. You're only going to have those which are defined by the non-zero singular values. So the way you can interpret ordinary least squares is as a projection of the original y in terms of some of the eigenvectors or the column vectors of the matrix U. And that means that we are taking away some specific properties. And when we go to ridge, we can actually see that some of these properties can be tuned to zero or close to zero by tuning this parameter lambda. So I'm just going to give you the, after the break, we are going to run these calculations because we would need also, there are some other small hidden gems in linear algebra, which we need in order to simplify that specific expression. So I wanted to bring in this just to give you some kind of deeper feeling of what these methods mean. And the thing which is interesting is that this singular value decomposition is also used widely in order to calculate the inverse of a matrix. And that gives you a stable matrix always. Okay, should we take a small break? Is that okay with everybody? I'm going to put the recording on pause.
Cool.